Hi everyone, my name is Wardul Hassan. I will be your instructor or lecturer for database system courses. So we will be following database system concept 7th edition. This week we'll be looking at chapter 1, the introduction. Uh, Please follow the canvas to look at your deadlines for your assignments, for your lab works and your quizzes. Apart from that, all the notices will be posted on Blackboard. If you have any questions, feel free to reach out to me using my email address. It's also available in Canvas and the syllabus of the course inside the website, Canvas website. Let's move on. So this is chapter 1, introduction for the database system concepts. Today, we're going to explore some real-world examples of how databases are used across different industries. Understanding these applications will give us insight into the significance of database in managing and organizing information efficiently. So, enterprise information in the business world, databases are critical for handling vast amounts of information. For instance, in sales, database keeps track of customers, products, and purchase histories. This allows companies to analyze buying patterns and personalized marketing efforts. In accounting, managing payments, receipts, and assets involve complex data that needs to be accurate and up to date. Databases help streamline these financial operations. In the human resources field, information about employees, including their personal details, salaries, payroll, taxes, is managed using databases. This ensures efficient payroll processing and compliance with tax regulations. Manufacturing, in manufacturing, managing production, inventory, orders, and other supply chain requires real-time data to optimize operations. Database provides a necessary tool to keep track of track of materials, products, and orders efficiently. In the banking and finance sector, database plays a crucial role in handling customer information, accounts, loans, and various banking transactions. For example, banking transactions um, include every transactions, whether it's a deposit, it's a withdrawal, or a transfer, is recorded in a database. This ensures accuracy and provides a detailed transaction history for customers. Credit card transactions, this enormous volume of transaction made via credit card is managed through databases, which help detect fraudulent activities and ensures smooth processing. In the finance world, databases are used to manage the sales and purchase of financial instruments such as stocks and bonds. They are also real-time market data, which is essential for making informed trading decisions and all. In the universities, higher education institutions uses database to manage student information like course registrations and grades. This helps in organizing data about students, academic progress, course enrollments, and ensuring academic record keeping. As you can see, databases are fundamental to many aspects of modern life and business. They enable organizations to store, retrieve, and analyze large amount of data efficiently. This in turn helps the organizations make informed decisions, improve customer service, and maintain smooth operations. In anything that you use today uses some sort of database. Let's look at some more examples how databases are used in different fields. These examples will further demonstrate the versatility and necessity of databases in organizing and managing vast amount of data. Let's look at the airline industry. For reservation and schedules, airlines uses database to manage flight reservations and schedules. Every booking a customer makes is recorded in a database, which helps manage seat availability and passenger details. Additionally, flight schedules, delays, and cancellations are tracked, providing up-to-date information to customers and airline staff. Telecommunication, so call records and billing. Telecommunication companies maintain extensive database of call records, text messages, and data usage. This information is crucial for generating monthly bills for customers. In the case of prepaid calling cards, databases are used to track the remaining balances based on usage. Web-based services. The rise of internet has led to a significant increase in web-based services that rely heavily on databases. Let's explore a few examples. Online retailers like e-commerce platforms such as Amazon use databases to track orders, manage inventory, and provide customized recommendations based on customer browsing and purchasing history. This helps in personalizing the shopping experience and involving customer satisfaction. Online advertisements, such as websites and platforms, use databases to manage and display targeted advertisements. These databases store user data, browsing patterns, and preferences to deliver ads that are most relevant to each user, thereby maximizing ad efficiency. Now, let's talk about document databases. Document database is a type of NoSQL database. We call it NoSQL database designed to store, retrieve, and manage document-oriented information. These databases are particularly used for applications where the data is highly varied and doesn't fit nearly into tables, such as managing unstructured data like emails, XML documents, and JSON files. Navigation systems, such as those used in GPS devices and mapping applications, rely on databases to maintain the location of various points of interest. They also store detailed information about the routes and roads, train systems, buses, and more. This data helps users to find the best routes, estimate travel times, and navigate efficiently. These examples illustrate the diverse application of database across various industries. Databases are not just about storing data, they are about organizing it in a way that it makes accessible and useful. As we delve deeper into the database systems, we will learn about how to design, implement, and manage databases efficiently, enabling us to handle the real world data challenges. Now that we have seen various applications of database, let's discuss why database systems are essential. Historically, many early database applications were built directly on top of file systems. However, this approach led to several significant problems. Let's go through them. Number one is the data redundancy and inconsistency. When data is stored in multiple file formats, it often results in duplication of information across different files. This redundancy can lead to inconsistencies because of if one copy of the data is updated and others are not, the information becomes unreliable. For example, if customers informed is stored in multiple places, information is stored in multiple places, a change in address might be updated in one file but not in others. Difficulty in accessing data. Accessing data in file systems can be cumbersome and inefficient. Each new task or query might require a program or script to be written. This makes the data retrieval inflexible and time consuming, particularly when new types of queries are needed. Number three is data isolation. Data is often scattered across multiple files and different formats. This makes it difficult to integrate data from different sources, poses challenges in creating a unified view of the information. And finally, integrity problems. Integrity constraints such as ensuring an account balance remains greater than zero becomes buried within program code. This means they are not explicitly stated or managed in a central place, making it hard to understand, maintain, or enforce data integrity. If there's a need to add a new constraint or change existing ones, it would require modifying the program code, which is not only inefficient but also prone to errors. These limitations highlight the need for a more structured approach to managing data. This is where databases systems come into play. They offer a more robust, flexible, and reliable way to handle data, addressing these issues effectively. Database systems reduce redundancy, ensures data consistency, provide efficient data access, and centralize the management of integrity constraints. As we continue, we will learn how these systems are designed to overcome the challenges posed by file-based data management. In this section, we are going to explore some critical concepts that underline the purpose and functionality of database systems, like atomicity of updates, concurrent access, and security problems. These are essential to understanding how databases maintain consistency, efficiency, and security. So atomicity of updates. Atomicity is one of the key properties of a database transaction, often summarized by the saying, all or nothing. This means that a series of operations within a transaction must either all be completed successfully or none of them should be applied at all. Example, consider a simple banking transaction where funds are transferred from one account to another. If a failure occurs halfway through this transaction, such as deducting the amount from the sender's account but not crediting it to the recipient's account, it leaves the database in an inconsistent state. Atomicity ensures that such situations don't occur. The transaction will either complete fully or be entirely rolled back. Concurrent access by multiple users. In many database systems, multiple users need to access and modify data simultaneously. This concurrent access is crucial for system performance, especially in large applications like banking, e-commerce, or social media platforms. So, issue uncontrolled concurrent access can lead to inconsistencies. For instance, if two people are accessing the same bank account balance of $100 simultaneously and both try to withdraw $50 without proper concurrency control, they may both succeed. This results in account showing an incurrent balance of 0 instead of 50. This phenomenon is known as the race condition and can lead to incorrect data being stored in the database. Database systems handle this through mechanisms like locking and transaction isolation levels to ensure concurrent transactions do not interfere with each other and lead to inconsistent data. Finally, security problems. Another significant concerns with the data management is security. Databases often contain sensitive information, and it's crucial to control who has access to what data. The challenge here is providing users access to some data while restricting them from others. From others can be complex. For example, in a company, managers might need to access the employee records, but certain personal information such as social security numbers should remain confidential. Proper security mechanisms need to be in place to handle these access controls effectively. Database systems provide robust security features, including user authentication, authorization, and data encryption to protect sensitive information from unauthorized access and breaches. Understanding these concepts is vital as they form the backbone of a reliable and secure database systems. As we continue with this course, we will delve deeper into how these properties are implemented and managed in real-world database systems, ensuring that our data remains consistent, accurate, and secure. Data model. A data model is essentially a collection of tools that help us describe several aspects of data. Let's break down these aspects. What is a data model? A data model provides a way to describe, number one is data, the actual pieces of information that we want to store, such as names, address, prices, etc. Data relationships, how different pieces of data relate to each other. For example, how customers relate to their orders or how students relate to the course they are enrolled in. Data semantics, the meaning of interpretation of the data. Understanding the context and purpose of the data helps us use it correctly. Data constraints, rules that the data must follow. This can include things like a student ID being unique or an account balance not going below 0. There are two types of data models. There are different types of data models. Let's explore the various types of data models commonly used in database systems. Number one, relational model. This is the most widely used data model today. It organizes data into tables or relations where each table consists of rows and columns. Each row in a table represents a unique record, and each column represents a field or attribute of that record. So we will look into it in details in the next slide, like how it looks, the rows and columns. The relational model provides a powerful way to manage data and relationships using a structured query language or SQL. It is known for its simplicity and ease of use in handling data relationships. Now, entity relationship model or ER models. The ER model is primarily used for database design. It uses entities, things we want to store information about, and relationships, how those entities interact with one another. For example, a university database, students can and courses could be entities, while enrollment could describe the relationship between them. The ER model helps in visualizing the structure of a database, and it is often used in the design phase to ensure that the database will accurately reflect the required data and relationships. Now, object-based data models. These models incorporate the principles of object-oriented programming. They allow data to be represented as objects, similar to how objects are used in programming languages. There are two main types. Object-oriented stores data as objects, which can include both data and methods that operates on the data. And object relational, a hybrid model that combines aspects of relational database with object-oriented concepts. And finally, a semi-structured data model. Unlike the relational model that relies on a fixed schema, semi-structured data models like XML allow for more flexibility in how data is organized and stored. This is particularly useful for data that doesn't fit neatly into a table, or for data that evolves over time. There are other older models, although less common today. It's useful to know about some of the older data models, like a network model. Uses a graph structure to represent relationship between entities. It is widely used in the past for complex data relationships. There was hierarchical model. So hierarchical model organizes data in a tree-like structure where each record has a single parent and possibly many children. This model was prevalent in early database systems, but has been largely replaced by more flexible models like the relational model. These various data models provide different ways to handle data depending on the requirements of the application. As we progress in this course, we will delve deeper into these models, focusing on how they are implemented and utilized in modern database systems. In this slide, we are focusing on the relational model, which is one of the most widely used data model in database systems today. The relational model organizes data into tables, which are also known as relations. Let's take a closer look at what this means and how it works. So the basics of the relational model. In a relational model, all data is stored in various tables. Each table represents a specific entity, and each row of the table corresponds to a unique record of that entity. Columns in the table represent the attributes of the entity. The power of the relational model lies in its simplicity and its ability to efficiently manage and query large amounts of structured data. Here we have an example table named instructor. This table stores data about instructors, and it has the following information or following columns or attributes. ID, a unique identifier for each instructor. Name, the name of the instructor. And then department name, the department to which the instructor belongs. Salary, the salary of the instructor. Each row for this table represents a record or a tuple. So each record, we call it a tuple as well, containing information about a particular instructor. For example, the first row represents an instructor with ID 22222 named Einstein, who works in the physics department and has a salary of 95 grands. These are just what do you say, imaginary numbers. Don't go on these numbers like Einstein's salary was actually this or not. I don't even know what Einstein's salary was. Another example is the row for cats from the computer science department earning a salary of 75 grand. So why do we use relational model? Data integrity and consistency. By organizing data into tables with predefined relationships, the relational model ensures data integrity and consistency. Each piece of data fits into a structured format, making it easy to enforce rules like unique identifiers and valid department names. Ease of use. The relational model is intuitive and straightforward, making it easy for users to understand and use. The use of standard structured query language or SQL allows the powerful and flexible data retrieval and manipulation. Scalability and performance. Relational databases are highly optimized for handling large amounts of data and can efficiently perform complex queries. This makes them suitable for a wide range of applications, from small-scale projects to large enterprise systems. The relational model was first proposed by E.F. Codd in the 1970s. It was since become the foundation of most modern database systems such as MySQL, PostgreSQL, and Oracle. The model's ability to represent data accurately and efficiently has made it a standard in the industry. This table is just a simple example, but in the real world databases, there could be many such tables, each representing different entities and their relationships. As we proceed, we will learn more about how to design these tables, define relationships between them, and use SQL to manipulate and query the data efficiently. To understand how relational databases organize and manage data, let's look at a sample relational database consisting of two tables, the instructor table and the department table. These tables illustrate how relational data can be structured and queried in a relational database. As we discussed earlier, the instructor table contains information about instructors. It has four columns: ID, name, department name, and salary. Each row in this table represents an individual instructor. For example, Einstein is an instructor in the physics department with a salary of 95 grands. The department table, the second table, department stores information about each academic department. It has three columns: department name, the name of the department, which is also present in the instructor table, the building where the department is located, and then the budget allocated to that department. Each row in the table represents a department. For example, the computer science department is located in Taylor building and has a budget of how many grands? How many zeros? 10 grand or 100 grand. Sorry, 100 grand. Anyway, relationship. We're not as rich as finance department anyway, but still is good. Relationships between tables. The key concepts of relational databases is the use of relationships between tables. In this example, the department name column is present in both the instructor and the department table, serving as a link between the two. This column acts as a foreign key in the instructor table that references the primary key in the department table. This relationship allows us to query related data efficiently. For example, we can easily find out which building an instructor works in or what the budget of the department is by joining these two tables using the department name column. So what are the benefits of using a relational database? We already went over this: data integrity, efficiency of data retrieval, and then scalability. So let's go over an example query. Let's consider a simple query. Find the names of the buildings of all instructors. We can use SQL to join the instructor and the department tables on the department name column and select the name and building columns. So the query can be select instructor.name, department.building from instructor, join department on instructor.department name equals to department.department name. This query would give us a list of instructors along with the buildings they work in, demonstrating the power of relational databases in managing and accessing related data. It's okay if you don't understand what the query I just mentioned and what it does or how it looks like. We will dig deeper into those in the next slides or next classes. You will have hands-on experience with writing queries and seeing how the data is shown. This will be a fun course. So the view of the data, understanding how data is organized and managed in a database system requires us to look at different levels of abstraction. This diagram represents a typical architecture for a database system, highlighting three levels of data views: the view level, the logical level, and the physical level. Let's explore each of these levels. The topmost level in the architecture in this view level, this level consists of multiple views such as view 1, view 2, up to view n. A view is a subset of database that is tailored to the needs of a particular user or a group of users. It provides a specific perspective of the data, often hiding the details that are not relevant to the user. Views are used to provide security by restricting access to certain parts of the database. For example, an employee might have a view that shows only their personal information and their department's data, but not the salaries of other employees. Uh, in a university database, a view of the student affairs department might show student names, IDs, and contact information, while a different view for the academic records department might show names, IDs, and grades. Number two is the logical level. The middle level is the logical level, which describes what data is stored in the database and the relationship exists among this data. This level abstracts away the details of how the data is stored physically. At the logical level, the database is described using data models, defining entities, attributes, and relationships. It focuses on the structure of the data without considering the physical storage aspects. The logical level provides a mere abstract view of the database that is independent of how the data is physically stored. It ensures that the database can be reorganized or optimized without changing the application program that interacts with it. The bottom level is the physical level, which describes how data is actually stored in the database. It involves the details of the storage, including file structure, indexing methods, and storage devices. This level deals with the physical storage of the data on disk and on other storage devices. It involves data structure and file organizations that help in storing and retrieving data efficiently. By managing the physical storage details, the level ensures the data can be accessed quickly and efficiently. It also provides the mechanism for data backup, recovery, and data integrity. So why do we need multi-level architecture? This three-level architecture provides several key benefits. Data independence, changes at one level do not require changes at higher level. For instance, modification of the physical storage structure do not affect the logical structure, and changes in the logical schema do not affect the views. Security and abstraction. Users can interact with the database through views that abstract away unnecessary details, ensuring data security, making it easier for users to work with the data they need. Optimization. Each level allows the optimization specific to its concerns. The physical level can be optimized for storage efficiency, while the logical level can be optimized for the data relationships and integrity. In database terminology, we often refer to instances and schemas when talking about structure and content of the database. To understand these concepts, it's helpful to draw an analogy to programming language where we deal the types and variables. Let's break down these terms. So schema, uh, the logical schema is overall logical structure of the database. It defines the types of data that will be stored, the relationship among different data items, and the rules governing these relationships. Consider a banking database that contains information about customers and accounts. The logical schema defines entities such as customer and account and the relationship between them, like each customer can have multiple accounts. In programming, a logical schema is similar to type information of a variable. Just like a variable type defines what kind of data is the variable can hold, the logical schema defines what kind of data the databases will manage. Physical schema. The physical schema describes how the data actually stored in the database. It includes detail about the file structures, storage path, indexing methods, and other aspects that determine how the data is physically organized on storage devices. The physical schema is concerned with optimizing data storage and access efficiency. It provides the blueprint for storing data in a way that maximizes performance while minimizing storage requirements. In programming, while the logical schema is like the type definition, the physical schema is akin to the memory layout of that variable. It defines how that data is physically arranged and accessed in the memory or storage. An instance refers to an actual content in the database at a particular point in time. It is a snapshot of the data stored in the database, representing the state of the data at that specific moment. In our banking database example, an instance would include specific details like customer names, account numbers, balances, and transaction histories. These details change over time as transactions are made and customers update their information. In programming, an instance is like the value of the variable at a given point in time. Just as the value of a variable can change, the instance of a database can change as the data is added, modified, or deleted. One of the essential features of modern database systems is their ability to separate different levels of data abstraction, which brings us to the concept of physical data independence. Let's dive into what this means and why it's important. What is physical data independence? Physical data independence refers to the ability to modify the physical schema without having to change the logical schema. In other words, changes to how data is stored physically do not affect how the data is logically organized or accessed by applications. Imagine a university database where student information is stored. If we decide to change the storage mechanism from the traditional hard disk to a mere modern SSD or reorganize the data files to improve performance, these changes should not affect the logical schema that defines the structure of student records or the way application query this data. Why is physical data independence important? Flexibility in optimization. Physical data independence allows database administrators to optimize storage and performance without disrupting the application that rely on the data. For example, they can change indexing strategies, move data to a new storage device, or reorganize file structures to improve performance without impacting the users or application accessing the data. Minimized disruptions. Applications depend on the logical schema to interact with the chain with the databases. By keeping the logical schema consistent, even when the physical schema changes, we ensure that application continue to function smoothly without needing modifications. Finally, scalability. As data volume grows or as the technology evolves, being able to adapt to physical storage to handle more data or to leverage new technologies is crucial. Physical data independence provides the ability to scale storage solutions without rewriting or adapting the logical schema. Let's talk about data definition language or DDL, which is used to define the structure of a database. What is a DDL? DDL is a specification notation used to define the database schema. It allows us to create, alter, and delete database structures like tables and indexes. Example of a DDL, here's a simple DDL statement to create table SQL copy. So create table instructor. So there's ID, uh, character 5. So this example is a query. This command defines a table name instructor with the 4 columns: ID, name, department name, and salary. The DDL compiler processes DDL statements and generates table templates. These templates are stored in a data dictionary which contains metadata, essentially data about the database's data. Importance of data dictionary. The data dictionary stores the database schema, integrity constraints, and authorization information. It defines constants like primary keys, example ID uniquely identifies each instructor and controls who can access different parts of the database. DDL helps in setting up the structure and rules of the database, ensuring data integrity and security. Data manipulation language or DML is crucial for interacting with the data stored in a database. It allows us to access and update data organized according to the chosen data model. DML, also known as query language, is used to perform operations like retrieval, insertion, deletion, and modification of the data in the database. There are two main types of DML: procedural DML and declarative DML. Procedural DML requires users to specify what data they need and how to get it. This approach involves detailed steps for retrieving data. And the declarative DML requires users to specify only what data is needed without detailing the steps to get the data. It focuses on the result rather than the process. Declarative DMLs are easier to learn and use. So declarative DMLs, also called non-procedural DMLs, are more user-friendly because they abstract the complexity of how the data retrieval is performed, making it simpler for users to interact with the database. So query language, the part of DML that deals specifically with retrieval information, is known as the query language. SQL is a common example of a declarative DML used widely for querying databases. DML enables efficient and effective data handling, allowing users to interact with the database to manage the data as per their needs. So this is first class. In our next video, we will cover the remaining slides or remaining topics covered in chapter 1. In the next video, we will end with chapter 1, and then we can have our evaluation like quiz and assignments based on chapter 1. So thank you.